So hello, welcome to day 2 of chapter 2. Um, just I want a few quick reminders. Homework 1 is due tonight. Now that's if you're watching this on YouTube, what tonight is would be different for you than possibly other people. So I was just phrase it as homework 1 is due at 11 p.m. on February 10th. So if today is February 10th, it's due tonight. If today is past February 10th, you missed the homework. Those of you watching me live, obviously that's tonight. Also, keep in mind your labs are due Thursdays at 3 o'clock. So you also have a lab due tomorrow, the 11th at 3. So homework Wednesday, 11 p.m. Lab Thursday, 3 p.m. So don't forget about those. The lab and the homework is all stuff from chapter 1. It's always going to be whatever I cover one week, the assignment for it is the next week. So all the stuff I'm doing now isn't due till next week. But this would just be on unit conversions and trig and significant figures. I know a lot of you already looked at it, so otherwise, unless there's any questions on shit like that, pause for effect. Is there? Was that a question? Sorry, I saw it unmute, but I didn't hear anything. I'll take that as a no, that wasn't a question, just an unmute. Okay, let's get into it. So what we've been talking about is the kinematics equations. We had those 3 equations that, you know what, I'm just going to go back a few slides real fast to explain all motion. And there was my email popping up. And what I said is this will explain all one-dimensional motion. What we're going to do today is we're going to talk about a special case of one-dimensional motion. See, this is for any acceleration of any kind. But I want to talk about the special case of free fall. And the short version is, if you're on Earth, which most of the time we're on, things fall down. This is, you come here for the really crazy ideas you didn't know beforehand. That on Earth, anything in the air will feel an acceleration downwards. Now, there are, things that are flying, birds, planes, rockets, whatever, have other things going on, but anything not powered, when let go, will fall down. And that's because it'll accelerate downward at a set rate. We define the acceleration on Earth as its own symbol of g. That g is just the acceleration due to gravity. And all things on Earth, assuming no air resistance, I'll come back to that, will accelerate downwards at a rate of 9.81 meters per second squared. That is the acceleration due to gravity. That I drop this ball, that's the rate it falls. Now, of note, traditionally, we define up as positive. And so what this means is something's falling downwards that has a negative acceleration. And what we'll say is the acceleration is negative g. I'm going to stress this right now. G is positive 9.81. Acceleration is negative g, or negative 9.81. But anytime you see the symbol g in an equation, you must put in a positive number. This is important. People like to make g negative, but g itself is positive. Your acceleration is negative g. And what I'm going to do is I'm going to take all of my kinematic equations, and all of them, I mean those 3, and I'm going to change them into a free fall mode. And I'm going to say for free fall, what that means is every place I had an A, I will put a negative G. And any X, I'm going to make a Y, because we're going to be looking at things moving in the Y axis. And so my 3 equations become this. Velocity equals initial velocity minus gt. Height equals initial height plus v naught t minus 1/2 gt squared. And v squared equals v naught squared minus 2g y minus y naught. Now, one thing that does change here. One thing that might change, that does change here is I said in x, you just define 0 wherever you want. You can do the same for y, but I always recommend making the ground of y equals 0. It makes your life easier. So, this is going to be true for anything in the air. So if I just take something and drop it, boop, when this drops, if I just drop it from rest means it's not moving. That means it'll just have an initial velocity of 0. If I drop something, I'll just say it accelerates down at negative g. I can use that to find how far it falls and everything. I'll just define upwards as the positive direction and use these kinematic equations. Well, my acceleration is, once again, negative g. I don't know why this went to another line. That's the general idea. But the thing is, this acceleration is true for any case. If I just drop this, I don't catch it. If I just drop this, it accelerates down at negative g. And when I just drop it, it means its initial velocity, it just means its initial velocity is 0. If I, instead of dropping it, take it and throw it downwards with some force, if I throw it downwards, its acceleration is still negative g. The difference when I throw it downwards is just it has an initial velocity. It has a negative initial velocity because it's going downward. And so, yeah, you drop something, initial velocity 0. You throw it downwards, you hit the keyboard. You throw it downwards, your initial velocity is just negative. But still, in both cases, my acceleration is negative g. My acceleration anytime you're in the air is negative g. If I instead was to throw something upwards, if I throw something upwards, I want this one, like so, my acceleration everywhere is negative g. That anytime something's in the air, its acceleration is negative g. The acceleration is negative g when it leaves my hand. The acceleration is negative g at the highest point. The acceleration is negative g at the lowest point. One interesting thing, though, if you throw something upwards, is that when something's going up, on the way up, on this pole, it's traveling up. That means its initial velocity must be positive because it's going up. And then it's going to hit some highest point and begin to fall. When it's falling, it's going down. Going down means it has a negative initial velocity. And if we're going from a negative initial, I misspoke. I said initial velocity. Going down means it has a negative velocity, not initial, just velocity in general. And if going up, it has a positive velocity, and if going down, it has a negative velocity, obviously it has to cross from positive to negative somewhere. Anytime you throw something up in the air, you can say its highest point is when it is in between going up and going down. And if you ever want to find the highest point, how high it gets, right about there, the highest point is always going to be at a moment where your velocity is 0 because you're halfway between going up and coming back down. That anytime something's thrown in the air, you ever want to find the highest point, you just find the moment where your velocity is 0. That's the highest point. But on the way up, it has a positive velocity. On the way down, it has a negative velocity. Good so far? Now, to make this slightly, not more complicated, but just something different, keep in mind velocities are at the highest point, but your acceleration is still negative g there. The acceleration is negative g anywhere. And we can talk about what happens when you throw something or whatnot. This setup right here is basically, again, me just doing this. Throwing this ball from some height, and then letting it go and hit the ground. I guess I don't really need to have it in slow motion, but we're going to do that anyways. And I can describe that motion by using my kinematics equations. I'm just going to say these 3 equations describe that motion. Now, as I said before, we do need to define a 0 point. Where is y equals 0? I like to always make my y equals 0 at the ground. Sometimes you can make it y naught. This figure to the right made y naught 0. I think it's always easier, as I said, to make the ground 0 because then you don't have to do negative heights. Because if I was to, when I throw the ball like this, you normally say that you throw something, like 1 meter above the ground. It then goes up and comes down and hits the ground. So it's easier to say that the ground is your 0 because that's your lowest point, and that your y naught is whatever that height is. It just normally makes life easier. But since a equals negative g everywhere, we can go and look at how long it takes to hit the ground and things like that. Now, one neat thing here, because acceleration equals negative g anywhere, that if I throw this ball, and actually let's go to this video instead. If I throw this ball and catch it at the exact same height, I can instantly figure out exactly how fast it's moving when it hits my hand if I knew how fast it was moving when it left my hand. The reason why is because initially it's going to have some upwards velocity. It's going to have some upwards velocity v naught. And that as it goes up, that velocity will be decreased. And my arrow is in completely wrong spot apparently, because I threw it from like there. And so what's going to happen is that velocity would decrease on the way up. But however much it loses on the way up, that's how much it's going to gain on the way down. At any given height, the magnitude of the velocity will be the same. The direction will be different. And like if I was to say this ball leaves this person's hand at 20 meters per second and the velocity here, if I knew the velocity here was 10 meters per second up, I could say the velocity here is negative 10 meters per second because it's down. When it leaves their hand at 20 meters per second, it comes back to the same height at negative 20 meters per second. It's symmetrical. This is kind of mildly obvious in mildly is at best with this equation on the basis that it's squared, right? That if you take the square root of something, there's two possible values, a positive one and a negative one. And this is saying as a function of height, v could be positive or negative. And that's true. That it could be positive on the way up, it could be negative on its way down. In fact, when solving for velocities using these equations, you often won't know which one it is, positive or negative. And you have to just go and logic out, is it positive or negative? Not from the math, but from actually doing it. By looking at it, being like, hey, it's on the way down. It must be negative. I'll show that in an example problem a little bit. Any questions there so far? Now, I'm saying everything falls at a rate of negative g. So I say, okay, let's say I got a hammer and a feather, and I drop both. Well, obviously they shouldn't fall at the same rate. If I take something like a feather or this piece of paper and drop it, it kind of slowly down. But here's the thing. That is only due to air resistance. Everything in the absence of air resistance falls at the rate negative g. It doesn't matter how much it weighs. It doesn't matter what its shape is. Everything without air resistance falls at that rate. This video I'm about to turn on is there we go, was filmed in the NASA Space Power Facility in Ohio, and is a huge vacuum chamber. So in this chamber, they sucked all the air out of the room, literally, and they're going to set with a mega speed trigger to at the same time drop a bowling ball and a bunch of feathers with no air resistance, and they filmed it in slow motion.
2, 1, release.
And without air resistance, these will fall completely in unison. Everything falls downwards at this rate of negative g, or accelerates downwards at this rate negative g. It doesn't matter what the things are. That is the acceleration of everything. Make sense? Like, it doesn't, if you want to see even me doing it, in this video, I took, I'm just going to put it over the text. I took a ping pong ball and a metal ball bearing. They have very different weights, and I dropped both of them at the same time. And you can see they fall in unison, even though they have very different weights. Everything accelerates downwards at a rate of negative g, with a rate of 9.81 meters per second squared downward. It doesn't matter what it is. Questions? Okay, let's do some problems. I like to, so I'm going to just a little bit about the class. I will always, as part of my PowerPoint, have example problems. These problems will just be right in the PowerPoint, and they're often old exam problems. I'm also, the homework has old exam problems, and also, I'm going to wait to the end, and then I'll talk about Friday's class. Let's not get ahead of myself. So let's look at some problems. This first one is not an old exam problem, but it's from a textbook, and I read the problem like, what the hell are they talking about? I had to look it up, and I think it's so goddamn silly. I always do this problem each year, and it says a springbok is a type of antelope, and they get their name for their jumping ability because they do something called pronking. This is what pronking looks like. I think it looks kind of silly. So, springboks, how they work, how they pronk, is what they do is while they're on the ground, they should be four legs, but whatever, I'm doing two. They crouch their legs and push off into the air. And so what happens is that when they're pushing off, they're accelerating upwards. That is going to continue for the entire time they're extending their legs. And I say here that time period, as they extend their legs, they accelerate for 35 meters per second squared over a distance of 0.7 meters. That's just that. Once they accelerate at that, they then leave the ground and go up into the air. And once they're up in the air, they're in free fall. With that information, at what speed do they leave the ground? And how high can these things get? Okay. So sorry, my computer is making a whole bunch of random noises that are probably going through there. I need to real fast do something. Okay, there we go. Those noises shouldn't happen anymore. So let's see what we know. Now my phone's making that noise. I'm saying in the first bit, I'm going to do a problem just for how fast they leave the ground of just them leaving. And I'm going to say just that part, when they go from heel, crouched, to heel before they leave the ground. Just that. For that time period, I say they accelerate at 35 meters per second squared, and they do that for 0.7 meters. So let's draw my picture and put those knowns up. I'm going to say they start crouched to a fully extended. In that period, they accelerate at 35 meters per second squared. I'm going to define the lowest point as 0, and when they leave the ground is 0.7 meters. And I want to say if they're going to start crouched, then jump. When they're fully crouched, they're not moving. I mean, theoretically, they're jumping. You could argue that they might have some velocity, but at the lowest point, they're in between going down and going up. They shouldn't have any velocity right there. Now, this is not free fall. This is not free fall because my acceleration is 35. It's not 9.8. They're not in the air here. They're just doing squats. And so I'm not going to include my g's into the equation, but I still leave it in terms of y because we're going up and down. And I'm going to say, what's the velocity to leave the ground? What's v? So there's my notes. A, y naught, y, v naught, and I want to find v. When I look at these, I say, hey, I don't know t. I don't know t. And since there's a t here and here, those top two equations can't be used. I have to use this equation. And so that's how I know that's the equation to use. It's the only one that matches. And so I'm going to say, okay, I want to find v. I'll just take that equation. Now, and this one's already solved for v squared. I'm not going to bother rearranging because it's solved for v squared already. I'm just going to plug right in. And square root. And what I'll say is if they accelerate at 35 meters per second squared for 0.7 meters, they leave the ground at 7 meters per second. Any questions there? Okay. Now let's do the actual free fall thing. So I'm saying they crouch and push off. And because they push off, right when they leave the ground, they're at 7 meters per second. And they go pew up into the air. And I say, how high do they get? What's their maximum height? So I'm going to redefine some stuff. And I'm going to say, okay, let's just change my y naught equals 0. And let's just update it. Let's just say, new problem, say instead of this my 0, let's make this my 0. Because, I mean, why not? I want to know how high off the ground they get. So why not go from there to there? So I'll say right there, that's going to be my 0. Now though in free fall, so now my acceleration is negative g. That g should be italicized. I'm going to fix that real fast. You always get to see which equation I'm using. And I can say, okay, they're leaving the ground at 7 meters per second. Now, if I want to find the highest point is always where your velocity is 0. And so I say, okay, I'm going to claim v equals 0 and solve for y. The thing is, I still don't know time. And since I still don't know time, I still have to use the same equation. But now I'm just going to say, instead of starting at 0 and going to 7, now they're starting at 7 and going to 0. And then now, instead of an acceleration of 35 or whatever it was, my acceleration will be negative g. And so I'll take this equation and say, okay, if I want to solve this, I want to solve for y. Now, I recommend never plugging numbers in ahead of time, except 0. Always feel free to plug in zeros. It makes things simple. And I'm going to plug in my zeros. V is 0 and y naught is 0. And what I did is I can factor, that makes my right side negative 2gy. And this is kind of a weird order. I subtracted v naught squared from both sides. I want to solve for y, so I'll just divide both sides by negative 2g, which cancels out my negative signs. And I'll get that the height they can reach is v naught squared over 2g. That the height they can reach is 7 meters per second squared over 2 times 9.81. 7 squared is 49. It gives me meters squared per second squared divided by meters per second squared. So the seconds cancel and some of my meters cancel. And I do this math. And I get that they can reach a height of 2.5 meters. Questions? Now I do say, does this number make sense? And 2.5 meters is like 8 feet tall. So the logical thing is, no, that doesn't really make sense. These things should not be able to jump 8 feet up. They can actually get surprisingly tall, like high. I mean, they can get not 8 feet, but a good 6 feet up. Air resistance is part of it. And also, they were numbers made to be easy for a problem. Textbooks don't put as much effort into their numbers as I do. Let's do another one. This next one is an old exam problem. And it's about Deadpool. In the first Deadpool movie, the opening piece of the movie is Deadpool jumping off a bridge into a car driving beneath him. And he kind of walks to the edge and hops off. Let's say Deadpool's slight hop off the bridge gives him an upward initial velocity of 2.21 meters per second. The bridge Deadpool starts on is 55 feet above the car below. What is his velocity when he hits the car? And how long is it till he hits the car? Basically, we're going to do this. Woo! So, let's look at what we know. I'm saying his initial velocity is 2.21 meters per second. Now, I say it's upward. Because it's upward, I have to say it's positive. And I also said he started 55 feet above the car. I like to always make the ground 0. So I'm going to say he's going to go from 55 feet up to the car. So I'm going to say he starts at 55 feet and he ends at 0. He ends at 0 because that's the ground. And I asked, what is his velocity when he hits the car? How long until he hits the car? Now, looking at this, I can say, okay, I got some things I know, but that why not is in feet, which is dumb because no, we got to work in metric. And so the second I see that 55 feet, I say, okay, I got to fix that. Screw 55 feet. Let's convert it. And so I'm going to say, okay, I did also give that 1 meter is 3.28 feet. So I'll convert this. I'll multiply by a ratio that cancels out feet and gets meters. And so 55 feet, what that really means is 16.77 meters. And so I'm just going to get rid of my y naught equals 55 feet, and I'm going to use that number. Now that I have my knowns and my unknowns, now I play my matching game. And I say he's in free fall. From when he jumps to when he lands, that is free fall. I don't care that he started moving upwards. That is free fall. And I'm going to go and play the matching game. And so I'll look at this and see which equation. Well, let's color code it like I did last time, since I feel like I'm going a little fast. V naught we know. V naught is in all the equations, so that's useful. Y naught we know. There's no y naught in the top equation, but there is in second and third. Y, and I'm looking for V. Blue. V. So that's everything I know, not counting G. We know G. G is 9.8 meters per second squared. And what I can say is, hey, this top equation and this middle equation have this T term in them. I still don't know T, just like the antelope problem. Nothing changed since then, even though it's a completely different situation. And so it's going to be this equation again. It has to be that equation because that's the one that matches everything I know. And I say, okay, I want to solve for V. So I'll take this and put it aside and say, let's solve for V. Once again, I like to plug my zeros in ahead of time, and I said y equals 0. That means instead of negative 2g 0 minus y naught, I can just say that's negative 2g times negative y naught. And I'll multiply that through, canceling out the negative sign. And at this point, I might as well plug in. V naught is 2.21 meters per second. 2 is 2, g is 9.81 meters per second squared, and y is 16.77 meters. When I do that math, I get a value for v squared. And I square root and get 18.27. But here's the thing. If you were just to blindly do this and not just mathematical, just straight math, don't think physics, you'd say square root of 33.912 is 18.27. The answer is 18.27. But 18.27 is not the correct answer. It's actually wrong. And the reason why is physics isn't pure math. Physics is using math to explain the world. And I can say when he hits that call, he's moving downward. That he's not magically shooting up in the air when he hits something falling down. That makes no sense. And since he's moving downward, the velocity must be negative. You see, anytime you square root a number, there's two possible answers. It can either be positive or it can be negative. And most of the time, you don't think about that fact because most of the time, we don't work with negative numbers very much. But you're going to have to think about it here. If he is falling down, his velocity must be negative. And so his answer is negative 18.3 meters per second. Questions?
So
Yep.
I'm a little confused if when he jumped off, he moved up at first.
Yep.
Why y not is exactly 55 feet and
Because
not a
that's
little
where
bit.
he left the ground. I'm saying 55 feet is the height from right here, this ground, to the top of the call.
Okay.
If he's moving up, it means he wasn't at 55 feet for long. It means he started at 55 feet and then went up to, I don't know, maybe 60. I could work out how high up he went in a few seconds, but I'm not going to really bother.
Okay. Okay.
It means that that's just where he started. That go like this. That he started here and went right here was at 55 and then went up to something more before falling back down and going to less. Does that make sense?
It does. I would get the same, so the number would still be the same as if he didn't jump off, if he just walked off the bridge?
No, it wouldn't be.
Oh, okay.
Because
Why wouldn't?
if he just walked off, that would mean he'd have no initial velocity. And having no initial velocity would mean that this term right here would be 0. And if that term right there was 0, you'd get a different number. What would be the same, and this doesn't really make any sense physics-wise, so just bear with me, is if he jumps up there at 2.21, or if he somehow rocketed downward at negative 2.21 initially, that would be the same. Because keep in mind, it's a parallel thing. And so if right here, if his velocity is 2.21, that means right here on his way back down, it's negative 2.21 meters per second. And so that would be the same if he rocketed downward though, because we're squaring at this point. But
Okay.
if he started with 0, this term would have gone away, changing the value.
All right, that's perfect. That's perfect. Thank you.
Cool. Now, I said before, this is an old exam problem. On the exam, a shit ton of people forgot that negative sign, and they left it as positive. And I'm going to tell you right now, I only took off like 2 points for that, but it really screws you up on Part B. Make sure you pay attention to that. Any velocity, is it up or down? Is it positive or negative? Pay attention to that. It's important. That being said, there was a Part B. And Part B was how much time does it take? Now, going back to what I was just saying it was identical if he was going up 2.21 or down negative 2.2 and he goes off, that wouldn't change the velocity. That would affect this part right here. That would affect the time. And I would say, okay, now I want to solve for t. And I would say, okay, I know I can't use the bottom equation. I can't use the bottom equation because there's no t in it. So I'm not solving that for t. And so I have to use one of these. And the thing is, I can use either one because I know everything now but t. If I decided to use the middle one, or what was the middle one before I removed one, I get a quadratic. I'd have to solve the quadratic equation. I don't want to solve the quadratic equation. That sounds complicated. So I'm just going to use the top one. And say if I want to know how long it takes for him to hit the ground, I'll just solve for t. Or hit the car, not the ground. Because he goes in a car and the car spins. And say, okay, I want to solve for t. I added gt to both sides. I subtracted v from both sides. And then divided by g. And I'll plug in. Now note, my v is a negative 18.3. Once again, I'm going to stress that. So I have minus negative 18.3, and minus negative 18.3 is the same as plus 18.3. And I can do that math. Here's the fun thing. If you had forgotten that negative sign in point A, you would have gotten a negative value for time in part B. And a negative value for time is basically meaningless. A negative value of time means he hit the car before he jumped. That he jumped off the bridge and somehow went back in time. It doesn't make any sense. You should basically never get negative times unless you're doing with shit with time travel, which I wouldn't put beyond me, but I've never done before and hope not to. That would just be complicated. But that's how long. It's 2.09 seconds. If I remember correctly, I actually did this problem backwards. I watched the clip of the movie, timed how many seconds he was in the air. Then once I had that, made the numbers work to get this value. Questions on this problem? Let's do one more. The last problem I'm going to do today is also an old exam problem. And it was one of those things that I learned existed and thought it was so goddamn crazy I had to write a problem about it. That happens sometimes when I'm not doing comic books. But apparently there was competitive pogo sticking, and there is a record for who has the maximum height on a pogo stick. And as of the time I wrote this might not be up to date anymore. Two men, Biff Hutchison and Dalton Smith, were tied for the highest jump on a pogo stick, where they got 10.5 feet above the ground. Which, just like, think about that for a second, how high that is. Like, that's a full, more than a story on a pogo stick. It's kind of crazy, in my opinion. But these two guys, Biff and Dalton, got 10.5 feet above the ground on a pogo stick. My question is, what initial velocity did they need to leave the ground at to get to that height? Yep, nothing changed though. So let's look at what we know. I'm going to say they start on the ground, logically. So I'm going to say why not a 0? They started on the ground. And they went up 10.5 feet. Okay, right there, we got feet. You never want to work with feet. I got to convert that. But 1 meter is 3.28 feet. So I can convert my feet to meters by multiplying by a ratio and converting. And I'm going to say they started at the ground. They went up to a height of 3.2 meters. If I want to find the initial velocity to achieve that height, that 10.5 feet, that 3.2 meters, that's when they're at the highest point. Going back to, like, well, I did have a video of me throwing the ball down. Oh, that's to be dropping both things. That's going to be right there when it stopped moving. So that means that's my highest point. That's when my velocity is 0. I'm going to need to solve for V naught again. And so it's okay. That's what I know. At this point, the text is useless. The text is only there to give me the information. I say they start on the ground, they go up 3.2 meters at the highest point, the velocity is 0. What's their initial velocity? And I say, let's solve with that. And there's my figure. Note, I went from ground to ground. There's a reason for that. That'll come up later. And I'll say, okay, I'm trying to find velocity to reach the maximum height. We've already done a bunch of things with finding maximum height. And once again, I have no time. Just like the last two problems, I don't know t. So just like the last two problems, I need to use this equation. I'll be honest, I did this on purpose. All of these problems used this equation to start. One of them was something just going up and not worrying about going down. One of them was someone going up something and then down to the ground, and one was going pew, back to the same point. Makes no, what the problem looks like is not how you figure out which equation. How to figure out which equation is by matching your terms. And I say that has to be the equation because I don't know t. If I don't know t, I cannot use a t equation. And I'll say, okay, I'll plug in my zeros. V equals 0, y naught equals 0. I can then add 2gy to both sides. And then square root. And after plugging in my numbers, I can get the value. The answer is 7.92 meters per second. That's how fast they left the ground. Any questions on that so far? Now, as I said, this was an old exam problem. That's actually a little too quick for an exam problem. Your exams are traditionally only made up of 4 problems. I want to do this tab later, but I'll do it right now real fast. Your first exam will be 4 problems. The first one will be about Freefall. Like, it will be the first problem on the exam. This is a little too short for a problem. So there was a part B. And my part B says, how long did they spend in the air? What time period did they did it spend for them to start heal and do that to get back to heal? Now, if I want to solve that, I would say what they do is they're going to go from a height of 0 to a height of 0. Because how long they spend in the air means they're going to come, it's how long before they go from the ground to the ground. And I say, okay, that's what I'm going to solve. And I'll say, okay, we know y naught equals 0. We know y equals 0. We know v naught. I didn't write this explicitly. We're looking for t. So now I definitely want to use one of the equations with t in it because I'm looking for it. But I can say, you know what? I don't know v. That wasn't a given. And since I don't know v, let's use this equation right here. And I'll say, okay, plug in my zeros. That gives me 0 equals v naught t minus 1/2 gt squared. I can add 1/2 gt squared to both sides. But I got a t squared on one side, a t on the other. Let's divide both sides by t. If I divide both sides by t, one of them cancels out. I can multiply by 2, divide by g. And if I plug in my numbers, I get a value. Questions? Okay. When solving that, I blatantly lied to you at one spot. That is the correct answer. Everything I did there was 100% correct. But on this slide, I said something very not true. What I said is I can't use the top equation because I do not know v. But that's not true at all. I could have said that if they're starting on the ground and returning to the ground, if their v naught is 7.92 meters per second, if they're returning to the ground at the same height, their v final is 7.92 meters per second down. I could have said I do know the height. That v equals negative. That v and v naught were the same, just negative. That v equals negative v naught because they came and returned to the same height. And if I did that, I could have used that first equation. V equals v naught minus gt. And I'm saying negative v naught equals v naught minus gt. I'll subtract a v naught from both sides. Negative 2 v naught equals negative gt. And I'll divide both sides. Oops. And I'll divide both sides by negative g to get t equals 2 v naught over g. Sorry, I'll make that pop back up in a second. There's a reason I'm... Take a look. If I did that logic, I'd get time is 2 v naught over g. When I did it the way I did it, I got time is 2 v naught over g. It didn't matter which way I did it. That'll often happen in these problems. That if there's a part A and part B, there's often multiple ways to solve, especially part B. There'll normally be you need one equation to get A, and B and part B, you can use either of the other two. It doesn't matter which way you do it, and I don't care which way you do it, as long as you get the answer. Okay, so any questions there? Okay. That is the end of this chapter, which may lead you to say, but what about Friday then? And so I want to spend the next, not all of the 6 minutes I have left, but some of the 6 minutes that I've left, explaining how Fridays work in this class most of the time. There's some exceptions to this, but for most chapters, what of how Fridays are going to work. If we were in person, what I would have done is I would have on class on Friday brought a packet of problems. And on this packet of problems, let me just open up Vanco Hall real fast. On this packet of problems, I would have given you 25 minutes in class to solve the problems yourself. And then the second, why won't my, oh, because I'm drawing. And the second 25 minutes of class, I would have gone through the solutions. That's the way I like to do this. But here's the problem. Me giving you time in class to solve problems doesn't really work online. And so what's going to happen today and happen every other Wednesday, except for with one exception, is at exactly 2:50 today, when class should end, a PDF is going to open. This PDF is a series of problems. It's opening very slow. Some of them are old exam problems, and this one, this guy, and this guy, old exam problems. And what I would ask of you is sometime between now and Friday, take a look at them. Spend 10, 15 minutes and see if you can do them on your own. Practice is really useful. And then what I'm going to do is Friday at the beginning of class, the solutions will be posted. And then I will, on Friday and every other Friday, I will solve these problems live in front of you, walking through the answers, saying how I would grade them. And so after class Wednesday, please look at these examples, try your hand at doing them. Or, or on Thursday or on Friday. It doesn't have to be today. You have homework due tonight. Maybe do it Thursday or Friday. But on Friday, I will go through them. I will tell you what to expect on exams and what it's going to be like. And so that's how all chapters but chapter 4 would be like that. Well, lecture Monday, then I'll lecture Wednesday, and on Friday, you'll get to see me do some problems on pen and paper using this guy. No PowerPoint at all. Make sense? Cool. All right, with that,
So I'm sorry. So we do those problems, we do them right now, or like whenever?
do them whenever you want. I'm not collecting them. You do not hand them in. I'm not collecting them. It is for your own practice. They're the type of problems you can expect on exams and homework. So it is for your practice and your benefit. If you decide not to do them, that is your decision. It's just not going to benefit you. But either way, I will show you how I do them on Friday. Friday's classes will normally only be 25 minutes because traditionally I spent 25 minutes having you guys do problems, the 25 minutes me going through them. And I decided not to change to add more problems because we're online. And if you are spending time outside class, I want to kind of reward that. So Friday's class would just be me going through them. But I'm not collecting them. They are not due. They are for your own benefit. Any other questions?
Where do we find those example problems?
I have them set to show up at 2:50 on each Wednesday. So you can see here, like February 10th at 2:50. So they will show up when class ends. So like theoretically it should be there already, but it's not because, it'll show up when class ends, but I said when class ends. So just like reload in 2 minutes and it will be there.
Okay, thank you.
No problem. Okay. There they are. Oh, and for those of you who are watching videos, the video links to the YouTube page when I do example problems will not be up here in the lecture notes. What will be down here next to the solutions, which will become obvious once I start posting them. But other than that, is there any other questions? Okay. Have a good day. Once again, homework due tonight, lab due tomorrow, and Friday we'll do example problems. I'll see you then.
Thank you.
Thank you.
Gracias.